Nice. Hello, everybody. I'm Dovydas. So excited to be here again. A quick reminder to all of the members of the Lithuania's AI Association. We have our global members meeting this Thursday. And now I'm switching back to Lithuanian. Sveiki visi. Mes turėsime visuotinį narių susirinkimą šį ketvirtadienį. Tiesiog primenu visiems asociacijos nariams. Ir noriu pakviesti čia Kamilę, kuri papasakos mums apie tai, kaip galime panaudoti mašininį mokymąsi ir dirbtinį intelektą, ne tik versle ir ne tik skaičiuojant tabular data, bet ir dirbant su gerokai įdomesnėm problemom. Ir ji papasakos, kaip mes galime jį panaudoti astrofizikoje. Neutron stars, right? Ok, tai perduodu mikrofoną tau.
So hi everyone, nice to meet you. I'm Kamilė Lukošiūtė. Thank you for inviting me. So I'm currently a PhD student in physics at the University of Amsterdam with a research focus in astrophysics and cosmology. And I'll be telling you about one of the ongoing projects that I'm leading that we recently published a workshop paper on at NeurIPS. So although my research is in astrophysics, I'm mostly interested in bringing techniques from other fields into astrophysics that would be truly useful for accelerating discovery. So I'm often thinking about, okay, like what techniques are actually useful, and yeah, how do I incorporate that into my research? Not in a way that's just like fancy and fun, but also impactful. So this particular project involves, modeling neutron star mergers, the light signals from neutron star mergers, using variational autoencoders. So first, I'll tell you some of the physics behind neutron star mergers and why neutron star mergers are really awesome, in my very biased opinion, and how measurements and discoveries are made in this field, and then how we are applying machine learning techniques to accelerate discovery. So let's begin with some astrophysics. This little video that we are about to see illustrates the merger of two neutron stars, first emitting gravitational waves, and then showing the explosion that comes afterward. So when a system of two heavy objects containing black holes, or neutron stars, start spiraling toward each other during a merger, they generate gravitational waves, which are ripples in space-time itself that appear when the masses are accelerating. And since 2015, we can observe these gravitational waves with instruments such as LIGO and Virgo. So in the case of neutron stars, after the gravitational waves are emitted and during, they exert really strong forces on each other and literally rip mass from each other's surfaces. And then the stars merge, become one big black hole in the center, but then they've thrown everything out into space at really high speeds, and really this is just a big explosion and there's like a whole bunch of stuff flying around. So the ejected material that forms part of that explosion is really neutron-rich, neutron stars. And this environment is perfect for all of that material to undergo rapid neutron capture nucleosynthesis. So nucleosynthesis is the process of element formation. So you start with protons and neutrons, and you end up with like real elements. And this creates a whole bunch of unstable nuclei, radioactive stuff, and that decays towards stable elements. And this is how you form gold and platinum and all of these like fun elements. But you also have all these high energy particles floating around, which then get reabsorbed and re-emitted, and eventually get re-emitted as in the optical wavelengths. And we call that thing, that emission in the optical wavelengths, the kilonova. So to recap, kilonova is the thing that is the light signal that accompanies a neutron star merger. So we have only observed one of these things ever before, and that was in August of 2017. And we call that event GW170817. So here we are seeing two pictures taken by a telescope. So first, a few days after merger, and then about 2 weeks after merging. And this is a telescope in Chile. And the big blob in the center, that's the host galaxy. And then the little white lines actually show the event itself. And it's this little tiny thing. And as you can see, after 14 days, it's like almost completely gone and faded out of existence. So it's really only present for about 2 weeks. But when we actually observe a kilonova, that's not, like, we see these pretty pictures, but that's not the data that we analyze. We look at the light curves. So what are light curves? Most telescopes observe light through a filter, which selects some wavelengths, let's say from 2,000 to 4,000 nanometers, and integrates all of the energy over those wavelengths and filters out the rest. And what you end up with is a single data point at a specific time. So there's 6 subplots here, and each of them is a different band or color of light, and each of the little dots represent a given telescope observation at a given time. So x-axis time, y-axis brightness. I won't tell you yet what like the shaded bands are. We'll come to that later. There's a funny astronomical convention where smaller numbers are brighter and the bigger numbers are dimmer. So the y-axis is flipped, but I flipped it right side up. So you can interpret the usual up is bright, down is dim. So this is the data format that we look at when we want to understand the optical signals accompanying neutron star mergers. So the events themselves are really cool, and there are still many fundamental questions left unanswered about them. For example, we're not quite sure exactly what they'll look like. We don't know how much mass can be ejected. We don't know what the remnant always is, and we don't even know if they all look the same. But those are all the questions about the event itself. Observing these events can actually help us understand, the universe as a whole. So answering bigger questions, such as, did neutron star mergers create all of the elements in the universe heavier than iron? What goes on exactly inside of these stars, these rare and super dense objects? And lastly, my personal favorite, and what I think is a very important question, can we use measurements from neutron stars to constrain fundamental cosmological parameters, such as the expansion rate of the universe? So, brief step back for a note on the expansion of the universe. For about 100 years now, astronomers have known that all of the galaxies in the universe are moving away from us. And what that really means is that the universe in between our galaxy and another galaxy is expanding. And so this is a little bit weird if you're hearing about it for the first time, but it's like, casual stuff. So one natural question to ask is, well, how fast is it expanding? What's the, is it speeding up? Is it slowing down? So answering this question with high precision has been the undertaking of cosmologists for a couple of decades now, not only because it's a natural question to ask, you kind of just want to know, but also because the process of answering the question reveals new information about the universe, and also reveals new mysteries, which are fun. So we call the expansion rate of the universe h0, or the value of the Hubble constant at the current time. And astrophysicists and cosmologists have gotten pretty good at measuring h0. So let's take a look at some of those measurements. So this plot here shows on the x-axis values of h0, that expansion rate I was talking about, in some funny units. There are many funny units in astronomy. And the green and orange bands show the two most constraining measurements of h0. First from the cosmic microwave background, and then also from supernovae. So the bands, the centers, show the 1 sigma uncertainty level, and the outer bands show the 2 sigma uncertainty level. So the green one first comes from measurements of the cosmic microwave background using the Planck satellite. And the cosmic microwave background is this really dim radiation that permeates the entire universe. And it's been around since about 300,000 years after the Big Bang. And by modeling small perturbations in the cosmic microwave background, you can infer a whole bunch of these cosmological parameters, and you can extract, for example, the Hubble constant. So that's the green one. The orange one, completely different method, comes from the SHOES collaboration, which is why it's labeled that, from measuring the distance to supernovae. Once we see a supernova in another galaxy, we can measure how redshifted the spectrum is, which tells us how fast it's moving away from us. And we also need to measure the distance, but we know that all supernovae are approximately like explode at the same like intrinsic brightness, and we can see how bright it is, so we can like estimate how far away it is. So the fun thing about these two measurements is that if you don't invoke any new physics, they should be the same measurement. These two values should be the same if there's, if you don't do anything crazy, or, if one of the groups did not get it wrong. And they absolutely do not match. There's actually like a 3 sigma discrepancy, and like they just don't match. And the data from these teams have been reanalyzed over and over again with the expectation that someone somewhere did something wrong. Just doesn't match. So yeah, this is like a really fundamental quantity in cosmology, and scientists just don't agree on the value, and like we would really like to solve this. So how could we go about solving such a discrepancy? So one option would be to just introduce a completely independent measurement, right? Something that's completely uncorrelated with the first two, and see if it matches one of the other two. So well, actually, observing the gravitational waves from neutron stars along with the kilonova signal that I mentioned before does give us this independent measurement. So the method is quite similar to the supernova method, but like different in a very important way. So first you see the kilonova and you can extract the redshift, but for the distance measurement, you use gravitational waves. So gravitational waves carry that distance information embedded in them, and so you have a completely independent distance measurement, and so you have a completely independent measurement of the Hubble constant, which these two things are needed to actually calculate the value. So that's actually what's plotted with this blue line. The posterior probability for H0, calculated from the data from that one singular event we saw back in 2017. And the method's not great, as you can see by this like enormously wide posterior. And there's like a number of physical modeling uncertainties, but this method can only get better as we observe more and more events. So that's what we're hoping for. So before I move on, I want to briefly discuss how this blue line is like actually constructed. Because it's actually how like measurements in astrophysics are made all of the time. So we build a physics-based model for what some observable would look like, given some parameters, for example, H0, and then you try to compute the probability of those observations given that parameter. And you do this for a whole bunch of these parameters, and you try to match it up against the real observable that you have. And then, you say like, okay, this is the one that's most likely, and that's probably like the true parameter of the universe. So to construct this probability density, you basically just need to draw a whole bunch of samples. For those of you that know things like this, this is done like with like Markov chain Monte Carlo or nested sampling methods. And you need to do the sampling like a couple thousand times. So the point is like you have to evaluate your model a couple thousand times kind of fast. So it's not a huge amount of sampling, but like the point is that a factor of 10 can like really speed up your analysis. And there are many steps in models for something like kilonova observables to Hubble constant, but one of the ones that I work with is going from kilonova properties, so like properties of the ejected material itself, to kilonova observables, because we need to understand what that light signal is actually going to look like if we're going to extract the redshift. Oh, it's small. The kilonova properties are things like how much mass was ejected, how many different types, how fast is it moving, what's it made of, how is it distributed, so like all of like the information about like this explosion. And these properties will ultimately determine what telescopes observe. So what telescopes observe is like done in 2 steps. The first thing you do is use a simulator to compute the kilonova spectrum, which you go from these properties and then you use a simulator to basically say, okay, how much energy is being emitted at a given wavelength at a given time. So that's what the 3 plots in the center, I'm showing some examples of spectra, where on the x-axis is like some wavelengths and angstroms, and on the y-axis is energy at 3 different times. So so the simulator, that's all good. And then from the simulator, you can construct these light curves, which I was telling you before, you just integrate over like a certain wavelengths of light in order to get those data points. So I have a simulator and I know how to integrate. So that means I can create all of these samples, right? That I need, like all these samples to so I compare with my data to get my universe expansion rate, right? Well, it's not so simple. So the problem is that our simulators, the really accurate ones, are really, really slow. They take a few hours for each parameter set. So naturally, this is way too slow for any sampling-based algorithm, and we need to find a way to work around this. So, what to do? Option 1 would be to just use a simpler model that's not nearly as accurate, but like scientists don't really do that because the models end up being really quite inaccurate and like not representative of the events themselves. So another thing you could do, which is like what I'm much more interested in, is to build a surrogate model. A model for your model, if you will, where the new model just runs a lot faster. So so I'm trying to build a data-driven model for a physics-based model. And the usual way of doing this in the astrophysics community is to just build something with Gaussian process regression. Now, Gaussian process regression is all fine and good, but the main problem with it is that this method requires using the entire data set at prediction time. So if you have a large data set, your prediction time scales with the size of the data set. And this gets unbearably slow, even for me, even where my simulation sets are not even that big. So I thought, okay, neural networks probably can make a pretty good surrogate model, but evaluate faster. So, if I can build a surrogate using some sort of like neural network-based architecture, I can, enable a whole bunch of new physics analyses. So that's what I set out to do, to try to find a neural network-based architecture that would be a suitable model for my simulated kilonova data. So after experimenting with various architectures, I landed on using a conditional variational autoencoder to use for my data-driven surrogate model. So the conditional variational autoencoder works as follows. So both the encoder and decoder are 2 neural networks. The first thing you do is you take a given data example, so for me that's a spectrum, and you append it with what I've labeled X are the physical properties, and you pass it through the encoder. The encoder outputs the parameters of a multidimensional Gaussian, which is supposed to represent a probabilistic latent space, and then you sample from there, and then you append the physical properties again, pass it through the decoder neural network, which is supposed to learn how to reconstruct the original spectrum. And then after training, I can always just throw away the encoder, and then what I have is a model that takes some random sample Z that represents noise for me, really, and takes input parameters X, and what you get out is a representative spectrum. So in this way, it's a model that can generate high dimensional data really fast. And yeah, this is actually exactly what I was looking for. It's a data-driven model that can quickly predict these spectra so that I can use it in sampling analyses. And yeah, I can sample from a continuous range of input parameters, and there's no need to simulate every single time you need to take a sample. So I've trained the CVAE on several different kilonova simulation datasets, and it's fast and it works well. So what I'm showing here are 3 test spectra, and at 3 different times. So on the top, 0.2 days, in the middle, 4.2 days, and the bottom, 14.2 days. And the orange lines are the original data, and the purple are my CVAE outputs. And like, if you look by eye, you're like, okay, like the bumps, like it's not perfectly predicted. But the thing is, all of that is noise. Like, I know how the simulator introduces noise, and what the neural network is doing is like learning how to recreate the distribution of noise. And so B and C look fine. I have cannot forgive A for being so bad, but the thing that's happening there is that the first data point is pretty much always poorly predicted, because it's a little bit probabilistic, whether at the first data point the explosion has occurred or not. So there's like a lot of uncertainty there. But it also doesn't really matter, because at t equals 0.2, that's about 4 hours after merger, we're not likely to have any observations 4 hours after merger, because it takes, when a kilonova happens, you actually need to spend time hunting for it with your telescopes. So we're not likely to have observations that early, and so I'm not worried about it. So the spectra look good. However, as I said before, astronomers don't really look at spectra when they're looking to analyze these events. So they look at the light curves. So the next thing I did was, look at the errors in the light curves. So here I'm showing, again, 3 test examples from constructed from spectra, where the solid lines show the CVAE, like my surrogate models, outputs, and the original data is shown in the dashed lines. And below, I have like the absolute difference between the prediction and the original model. So yeah, one thing to note is that there's like, it's a negative log on the y-axis, so there seems to be like huge deviations at later times, but those deviations are much smaller in reality because of this log. So so this looks pretty good to me. And the next thing to think about is like, okay, this looks good to me because like, I say like, okay, like it's almost in most cases reconstructed, but like, what does an astronomer think? One of the heuristics that astronomers use is, okay, like if it's plus or minus 1 magnitude, you're not really introducing any error. And that's why I have this like delta M here to look for like, okay, when is the error greater than plus or minus 1 magnitude? So the main thing for me was that we really thought a long time about what kind of error measurements would be most informative to astronomers and would give us an understanding of the errors that introduced by the surrogate, as it applies to like the end goal of doing science. So this is important for me because, yeah, you can do like fancy machine learning, but you also need to demonstrate that it's meaningful to a particular field. And you need to demonstrate the usefulness of these techniques. And so in my case, devising methods for physically meaningful error measurement was exactly this. There's more details about the error analysis that we did. For example, we look at the correlation of errors with input parameters and whatnot. And if you want more details on that, you can check out our physical sciences workshop paper. Yeah. So after establishing that our errors are not large and should not introduce any physical bias, we also try to evaluate the method by performing a representative scientific analysis using this method. So here on the left, I'm showing those GW17, 0817 data points again. And on the right, I'm showing the samples that were drawn from my surrogate model. So it's like the histogram like similar to that blue line that we saw before. And then what we do is that each of those parameters in those histograms like ends up being one like model line on the graph on the right, on the left, and yeah, so that shaded band represents like the set of all models from the parameter histograms. And so if you've ideally found like the correct parameters, you want the dashed lines, the shaded bands to go through the data points. And they do, sort of. There's errors that have nothing to do with me, but at minimum, this matches our expectations from previously published results. So another thing to note is that running the computation for these parameter histograms and creating this like parameter probability estimates, it takes like 5 minutes on my laptop. And this is something like a 400 times speed up over like what people were doing before using Gaussian processes. And so to me, this is really meaningful because it means we can do way more of these analyses and like extract way more information from these events. So this is just the beginning for our little kilonova model. And first we are moving beyond our proof of concept analysis using the surrogate model for real scientific analyses, and then eventually publishing those results. And I'm particularly excited by the work that's being done by my collaborator, Gerrit Rijmakers. And second, I believe in sharing good things with the community, so with the scientific community, so we've made our little surrogate model public, and I hope to encourage other scientists in using it because I think it's great. I think it's great for everyone. So, to recap, I told you about why neutron star mergers are really awesome astrophysical events and how they can be used to shed some light on some of the biggest mysteries in the universe, and also how we can use generative machine learning techniques to perhaps speed up the solving of some of these mysteries of the universe. So thank you for listening, and are there any questions? Yeah, so the comment was that for Gaussian process regression, you can use a subset of the data set in making a prediction. But if you want like a fully accurate prediction, I think you do need to use the full data set, right? Okay, I mean, I'm not a Gaussian process regression expert, so I'll take your word for it. Yeah. Yeah, so the question was whether or not I compared with other generative models, such as GANs or diffusion models. So the first thing is that the groundwork for this project was done like almost 3 years ago now. So like the big thing at the time was VAEs and GANs, and I did test GANs for a little while. So the fact that it's a conditional variational autoencoder makes it a slightly more difficult because, yeah, conditional GANs are weird. But I did test these things out. I had some trouble with, yeah, as training GANs is difficult, and this worked. I was also drawn to like some of the sort of, so in the end, the VAE ends up being a non-probabilistic method because of like some discrepancies in like how VAEs are written down on paper versus how they are in training and practice. Like here, they're not fully interpretable. For Gaussian outputs, it's like a whole thing that like breaks my heart. But like I really wanted it to be a probabilistic method, and that's why I was more drawn towards this. So to answer your question, I did test out some other models. I did not try out diffusion models, but again, at the time, like, I was also mainly focusing on like getting something fast to work and not necessarily like the best thing. If this had moved forward, I would have tested more stuff. Yeah. So I think that's, I mean, I've never really looked at the latent space because again, I didn't really care about it. So I mean, when people do usually use VAUs for stuff, they do care about what's encoded in the latent space. But like for this purpose, like what I'm really looking for here is an architecture that like can generate big stuff. You can't just say, build me a feed-forward neural network that goes, from 4 parameters to 2,000. Like that just doesn't work. That's untrainable in practice. I don't know what's encoded in latent space. I never looked. Also because at like inference time, I also like don't sample from the latent space. I sample, I just sample from what the latent space was regularized to. If I had to guess, it's like the distribution of the noise. Like I said, like the distribution of the noise is learned because it is slightly dependent on like wavelength, for example. Yep. So it's a stochastic simulator. So the way the simulator works is that, so the way the simulator works is that it sets up a system where you have a whole bunch of photons like moving through space, like moving outwards through a cloud of gas. And how do you model like a cloud of photons? You have some tracer photons and you like basically like count them as they move and you count their actions. But photons, are quantum mechanical particles, and so the actions that they take are probabilistic, and so what you end up with is like not exactly the same trajectory each time. And so that's like one source of noise that shows up, that like the paths taken by the photons are not the same throughout the simulator. And the second thing is that like there's an additional amount of noise where it's like photon counting noise. Like when we observe these signals, like we get like a high amount of photons, but like in the simulator, you're literally counting. It's like, was there a photon or wasn't? It's like 0 photons or 1 photons. So because of the stochastic nature of the simulator, that's like where it comes from. And there is a way to understand that noise. It's just that like the guy who writes the simulator like isn't super keen on sharing his code. So I never got to look at it, so. Yeah. Yeah, so that's a good question. So the question was, if I'm measuring the success of my model against light curves, why am I not generating light curves? Every single telescope in the world has a different set of bands. So here, in this plot, I'm showing I, Z, Y, J, H, and K. There's like literally hundreds of different ones. And like you will have like one telescope band that will be like, oh, it ranges from 2,000 nanometers to 4,000 nanometers. And a different telescope will have a band that's like, actually, ours goes from 1950 to 2,400. And then they'll call it the same letter. But the thing is, if you really want to compare with real telescope observations, like you have to know what the observable is in that particular band, as is defined by like literally like a piece of plastic that exists somewhere like in Chile, right? So because there are so many different bands, I wanted my model to be able to use and how does like anyone ever use which telescope observations to use or like to like make mocks of? They pick their favorite one, whatever collaboration they're in. There's like no rhyme or reason to it. And so basically I wanted this tool to be able to use by everyone for whatever their favorite telescope is, for whatever observations like ultimately show up, because like you never know which telescope is going to see it first. There's like a fun competitive aspect to it, like who gets the first observations. And so yeah, the reason I generate spectra is because from the spectra you can create all of the telescope bands observations, like every single one. We just need to have like a description file which specifies what the band looks like. Yeah, that's mainly it. I wanted it to be like pretty agnostic. Yeah. If you can simulate it, yeah. So I actually have seen a paper for this particular, like they sort of, I mean, the question is, where do you simulate next such that you have, okay, I should repeat the question. The question was that since my data comes from a simulator and I have infinite data, maybe there's a way to test, I guess maybe your question is where one should simulate next in such so that it is most efficient for whatever observations you will end up taking. That's one question to ask. Yeah, you could also say like, where should I simulate next so I can reduce the noise in some particular like scientific analysis, or like in some part of the parameter space of the analysis. So these things, yeah, people do this. Not for my surrogate, but like for general surrogates. Like, so yeah. Yeah. We have discrete data points. Yeah, I mean, okay, sure. You have a discrete set of bands. I mean, but when you, for example, when you do like MCMC and you just set up a likelihood, you're really setting up like a point by point. Yeah, like. Yeah, that's not something I've done. So I mean, yeah. So to the crowd online, the question was, well, the comment was that perhaps it would be possible to combine, yeah, all of the observations like an n-dimensional space where n is the number of bands that you have. Yeah, that would work. Probably. But it gives you a continuous space over n bands, and you also never. So, for example, every single year, new telescopes are built, right? Do I include the new telescope bands? Is anyone going to use it? Who knows? I'd have to think about that more. But yeah. Yep. Could you repeat that? Oh, the Hubble constant. I mean, should I repeat that, or is the internet know that? Oh, okay, all right. You weren't asking me what's the purpose of doing science. Yeah, I mean, so, I mean, yeah, so I mean, so we need an accurate measure of the Hubble constant in order to constrain like the other stuff in the universe, or like the other problems that we have, like dark energy and dark matter. All of this is like also analyzed from a cosmology perspective using cosmological simulations. And so if you don't even like know one of the basic parameters, like what the value is, like all of your other values are going to be off, and you can't even answer questions like how much dark matter is there, because obviously like each of the parameters, cosmological parameters, have a complex interplay. So like the reason like I care about it is like I'd like to know about some of the like the dark stuff, the dark energy and the dark matter. I'd like to know what those mysteries are, and like one of the ways of approaching that is through cosmological studies and Hubble constant, like pretty big parameter in those models. Yeah. The question was whether or not the universe expands faster than the speed of light. I mean, not right now. That's it. This feels like an exam now, so I refuse to answer more than that. No, I mean, the current rate of expansion is not even close. But I mean, the rate is accelerated. It's accelerating. The expansion of the universe is accelerating. So I haven't thought exactly about like what happens when you get close to the speed of light. I haven't thought about that. Too scary, you know? I don't like thinking about the end of the universe. I didn't see it. Yeah. You mean absolutely no good reason? Yeah. I mean, yes. I will repeat the question. The question was, is the reason... Okay, I'll rephrase the question. Do astronomers like Gaussian processes because of the statistical elegance? Yes. Astronomers don't, from my experience, like astrophysicists are pretty reluctant to use neural networks, especially because they're like, oh, it's a black box. I don't understand it. And so there's something about Gaussian processes and like the fact that you can write it down and you can write down like this kernel matrix, and like they like that. They think it's like statistically interpretable, and that means like they feel like they can understand it. But I don't really. I think that this is entirely a feeling. Like it's I think it's there's no valid reason why. Oh, I don't understand how a matrix multiplication works. Of course, you understand how a matrix multiplication works, so therefore you understand neural networks. So I don't. Yeah. Statistical elegance. Astronomers are very attached to it. It's a good point. A kilonova? So that's a very good question. So the question is, has anyone predicted another kilonova to happen? So there is a rate at which they happen all the time. It's just like, I don't know what the rate is. It's something like 10 per gigaparsec volume cubed per year. So like within some volume, how many happen per year? They happen whether or not we're looking. We haven't been looking. The LIGO and Virgo detectors have been shut down, and they were shut down early because of COVID. So these events are too dim to just point telescopes at. And the way that it actually works, that when you're observing them, is that you get a signal from the gravitational wave detectors, and they say, hey, like we saw some gravitational waves, you should like point your telescopes like in that general direction, and you have to go hunt for them in this like, giant region with your telescopes. Well, if LIGO and Virgo are shut down because of COVID, and they're starting up again, I think like in a few months for the new observing season. But yeah, it's been a couple of years since they've been operational, so we just haven't seen them. They've been happening. Just haven't seen them. Yep. The question was how long does the gravitational wave information take to reach us? Gravitational waves travel at the speed of light. So that's it takes as long as the number of light years times however long ago it occurred. These happen in other galaxies, so I don't know how many light years. The one event that we saw, GW 170817, is 43 megaparsecs away. You can convert that to light years. I don't know what that is in light years. So the gravitational waves are like minutes. Okay, that's not true. When the system is these two stars are in orbit, they are constantly emitting really weak gravitational waves. But the detectable range of frequencies that LIGO and Virgo can detect, seconds to minutes. So that happened, on August 17th, 2017, and then it faded out of view, let's say. And then the light from this kilonova, it took 2 weeks after that to all of it to arrive. There are other electromagnetic signals associated with this event. There's radio waves and X-rays, and there's a gamma ray burst, and all of them have different time frames. So if you look up in the sky, right now, it's been a couple years, you can still see the radio afterglow. So yeah, there is still, it's still up there. There's the mass is just floating around emitting radio waves. It's great. So there is still some stuff to learn. That's a good point. But most of the exciting stuff happens in either seconds or a week. Okay. I don't see it here. Okay. Okay, I won't repeat the question because I imagine everyone online can read the question. Okay, so let me go back to that plot. The answer is yes. So, where does this uncertainty come from? The main thing is that the uncertainty in the measurement of H0 depends on the uncertainty measurement in the redshift, which is the speed that the object is moving away from us, and also the distance. And the distance measurement comes from gravitational waves, and there's this is actually a subplot, and the distance measurement coming from gravitational waves is correlated with the inclination angle. And the inclination angle is basically if you're looking at an object, are you looking at it from side on or the face? So there's a tilt there. So this, so that's where the shape of this comes from. It comes from the inferred value of because the quantity that you're actually sensitive to is the distance times the inclination angle. And the inclination angle is distance times the cosine of the inclination angle. So the cosine plus the actual measurement from the gravitational waves and all the noise in the gravitational wave measurement is what determines this shape. I hope that was a good answer, Pigling. My voice is running out, so I hope that's the end of the questions.
Was great. I'm so happy that we had so many questions today for you. So even you got your voice tired. Thanks everybody who was there online, and see you during our, as I mentioned before, our general meeting. So thank you all. Bye-bye.